All right, today is our final module within this unit. We are talking about cryptography. So, cryptography is the process of scrambling information into an unreadable form in order to keep it a secret. Anytime we are sending information over the internet, all kinds of people have the ability to see it and try to read it. Things like credit card numbers, our health records, our passwords, our bank accounts, or even just private messages that we're sending to other people. We don't want anyone but the intended recipient to be able to read that information. So we need to use cryptography to encode our messages before we send them. In cryptography, when we scramble information, that process is called encryption. And then when we unscramble it, that's called decryption. And the goal of cryptography, like I said before, we're trying to encode information so that only someone with verified authority, only the person we want to read our message, they have to have a password or a secret key, only they are able to decrypt the data on the other end of our sending. So a brief illustration of how general encryption works. So you've got some message, for instance, secrets. Do not tell anyone what this secret message says secretly. And we've got some random key full of just a bunch of nonsense. We're going to convert both of those to binary. We're going to push both of those through an encrypt function. We're going to pass our data and our key, and that will spit out some binary sequence that encodes basically a whole bunch of nonsense. So we're going to send that encrypted message to our recipient. They'll get that message in binary, and assuming we've agreed on a key beforehand, they can then decrypt that data using that key, and it will decrypt into the same message that we sent the first time. So this makes it so that you have to have this exact key in order to decrypt the message. Otherwise, your decryption will just result in more gobbledygook. You need to have the right key to get the correct decryption. So a historical example of cryptography, one of the oldest and simplest examples, is the Caesar cipher, which was used by Julius Caesar of Roman fame to send secret messages to his army. And because all of these messages were encrypted, if they ever got intercepted by an enemy force, they would not be readable, so their tactics wouldn't be revealed. The way the Caesar cipher works is each letter in the message is going to be shifted by a certain amount through the alphabet, and that amount is called the key. If I have a key of 1, the letter A becomes the letter B, the letter B becomes the letter C, C becomes D, etc. throughout the alphabet until we get to the end. Z loops around to the beginning and becomes A. With a larger key, we're going to shift further in the alphabet. So if we're trying to send the message go over there with a key of 4, that would result in, let's look at our alphabet. We've got the letter G. We're going to shift 1, 2, 3, 4. So G shifted by 4 gives us the letter K. That's our first letter. The letter O, when we shift by 4, we get the letter S. We have space, then we have the letter O again. V shifted by 4 is the letter Z, and so on and so forth until we get KS, SV, SZIV, XLIVI, which basically means nothing unless we know what the key is. So assuming that the person sending and the person receiving the message know what the same key is, the person on the other end could shift the other direction by also 4 to get that message go over there so that they actually know what they're meant to be doing. If I wanted to write some code to accomplish this, to do this encryption, I could say my message is whatever the user inputs. I could make a key of 3, and then I could make my secret equal an encrypt of that message with that key, and I can send that secret message to someone else. Now, we can use the Caesar cipher encryption algorithm if we want, but if we want to, we can use something more secure. So Caesar cipher is very easy to understand. It's a very simple encoding mechanism, but that also means that it's very easy to crack. It's very easy for other people to figure out what this encoding system is and break it. Now, the biggest problem with it is that there's only 26 possible keys to try. So if you know that they're using a Caesar cipher, there's not that many keys to try before you find the solution. And another problem is that you can only encode letters. You can't encode something like an image or audio or even numbers. Those are all invalid. So you can only do it with letters. So in today's cryptography, in which we are encoding all kinds of things, it's similar to Caesar cipher in that we're still encrypting data according to some key, and we're still gonna do some math to figure out what the encoding is. But in some differences, the math is gonna be much, much more complicated than just shift letters through the alphabet. And the key is gonna be much larger than the number 26, which is not very big. So if we are talking about encryption, we're talking about cracking encryption. Cracking is when an attacker is trying every single possible key, and if they do that, they'll eventually be able to decrypt your message, even if they didn't know the key beforehand. And in Caesar cipher, there's only 26 possible keys, which modern computers can crack in basically no time at all. 26 iterations is not a very long time. In the past of cryptography, 40-bit keys were used for normal encryption. And since keys are stored in binary, that means that there are 2 to the 40th power number of possible keys, which is about a trillion, 100,000, million, billion, trillion. So about a trillion different possible keys. But as computers continued to get better and faster, even these 40-bit keys weren't enough to stop hackers. They could guess all of the possible keys fast enough that it was worth it. So today's encryption algorithms use 256-bit keys. That means there's 2 to the 256th power possible keys, which is this ridiculously long number. And even with today's computing power, it would take trillions of years to try every single possible key. It's not a feasible task to try every possible key here. So different computing problems can be classified by how long it takes for a computer to solve this problem. And we want encryption to take computers a very long time to break. We want it to be a computationally hard problem, because trying every single key for a lock should take a very, very, very long time. It should be a hard problem so that our data stays safe, it stays encrypted so that hackers can't access it. In easy computational problems, increasing the size of the input is going to cause the time it takes to solve that problem to increase at a reasonable rate. So, for example, finding the smallest element in a list of numbers is an easy problem, because if you add one element to the end of the list, you only need to look at one more value to determine if it's smaller. So in this list, I have 1, 2, 3, 4, 5, 6 elements. If I add one to the end, I only have to look at one more thing. My time is going to increase linearly with the number of elements in the list. Each element, I'm going to add one more check, essentially. In computationally hard problems, solve time is going to increase at an exponential rate rather than a linear one. So cracking a large key is a very computationally difficult problem, because each time we add a bit, our number of possible keys is going to double. So if I only have 2 bits, that's 4 possible keys. If I have 3 bits, that's 8 possible keys. 4 bits gives me 16 possible keys, and so on and so forth. I'm getting double in size each time. So when I get to 256 bits, that's a frankly ridiculous number of possible keys. So if we look up at this graph, we have our possible number of keys to try. Everything between 0 and 10 is basically 0 because the scale goes up to 100,000. Once we reach about 15, 16, or 17, our number is skyrocketing. So we've hit 100,000 at about 17. If we keep going right on this graph, it's going to keep shooting upward and upward. So 256, this line is going to be super duper super high because it's getting twice as tall every single time we move once to the right. So some differences between 40-bit and 256-bit keys. 256 bits is roughly 6 times larger than 40 bits. So it takes up a decent amount more storage. However, it's not going to store 6 times more possible keys because each time we're doubling. So the number of keys is 2 to the 216 power more possible values. We're storing an astronomically high number more possible values in a 256-bit key than we were in a 40-bit key. Does that make sense so far? Cool. Okay. So cracking encryption is a hard problem for computers to solve because they're not able to try every possible key in a reasonable amount of time. And even if computers do get faster, all we need to do is increase the number of bits we're using to store keys, and that will increase our required time to solve exponentially. So let's talk about how we actually do sending of information via encryption. There's 2 main types. There's symmetric and asymmetric encryption. With symmetric encryption, both the sender and the receiver are going to use the same key to encrypt and decrypt the data. With asymmetric, one key is going to be used to encrypt the data, and a different key is going to be used to decrypt it. So let's look at an example of how this works. Let's say we have 2 people, Alf and Jeff. They've met in private, and they've decided on a private key that they are going to share with one another. So Alf says, let's use this key. Jeff says, yes, let's. So they both have a copy of the exact same key. If Alf wants to send a message to Jeff, Alf is going to encrypt their message using that key. They're going to send it over to Jeff. Jeff is going to use that key, decrypt the message, and read it. So both of them are using the same exact key. Now, the problem with that is that there are billions of devices on the internet. So every single computer can't privately meet with every single other computer to agree on a private key to use on both ends. So the current solution to this problem is called public key encryption, which is an asymmetric encryption system. One key is used to encrypt, and the second key is used to decrypt. So let's see how Alf and Jeff can do this public key encryption. Alf has both a public and a private key, and similarly, Jeff has their own public and private key. Every different device on the internet has their own public and private key. The public key is used to encrypt data, and their private key is used to decrypt data. When you receive a message that's been encoded using your public key, only your private key is able to unlock that message. As you might expect, everyone's public key is available for anyone in the world to see, but your private key is kept secret. Only you should have access to your own private key. So in this system, let's say Alf wants to send a message to Jeff. Alf is going to ask for Jeff's public key. Jeff sends over their public key. Then Alf will encrypt their message using Jeff's private key. Alf will send that message. And while this message is in transit, even if some hackers, if an attacker tries to access this method and they have Jeff's public key, which they probably have access to since it is a public thing, it's accessible by anyone, they won't be able to decrypt this message because only private keys are able to decrypt. Once it's been encrypted with that public key is not useful for unlocking. So once Jeff receives the message, they can use their private key to unlock the message and read it. Does that protocol make sense? Very generally? Cool, okay. And just a bit about password management, just so that you're all aware about how having a secure password affects you. So here's a little chart about how much time it takes for a hacker to brute force your password. Brute forcing is just trying every single possible permutation to just guess it. So if your password is only 4 characters long, doesn't matter what symbols you're using, you're instantly going to get guessed. 4 and 5 characters both not secure in the least. If your password is only comprised of numbers, anything up until 10 characters, instantly. There's no way a hacker is not going to guess your password if you're only using numbers. As you get up until 15, it can take up to 6 hours to guess. And as you add more and more characters, it's adding even more time. You can take up to 9 months if you have 18 characters with just numbers. Notice if we add lowercase characters, instead of having only 10 symbols to work with, now we have 26 characters. So we can have a shorter password and have it still be more secure because it's harder to guess. There's more possible permutations. And as we add more and more different types of symbols, if we move from lowercase to lowercase and uppercase, this is going to be even harder to crack because we've doubled from 26 to 52 different possible characters per slot. If we add numbers to that, it becomes even more difficult. And if we have numbers, uppercase, lowercase, letters, and symbols, it can take up to 7 quadrillion years for a hacker to brute force guess your password by just guessing every possible permutation of those symbols. So that's why it's good to both use a unique password for every thing that you access, because if a hacker gets your password in one place, they'll just try it in different places. And if you have the same password in multiple places, they'll just have access. And having a strong password that's long and mixes letters, both uppercase and lowercase, numbers and symbols, it makes it almost impossible to brute force crack your password. So there's all of that. Any last minute questions about encryption, cryptography, any of that? All right. Then let's do a brief discussion of our study guide. Today, we are just going to look over the very beginning and talk about the first unit. So our final exam is going to consist of 4 short answer and or programming questions, all of which are implemented within CodeHS. So all of the questions, all 4 of them, are on CodeHS. You should be able to see the semester 1 final module on CodeHS. It should be visible, but not accessible yet. Each of these sections is going to be worth 4 points for a total of 16 possible points. And you will have 45 minutes to complete all 4 parts of the exam. If CodeHS for some reason fails, I'm going to request that you type or write up your responses in a separate document, save that as a PDF, and then email that to finals@warriorlife.net. So just in case, I would request that you do this in addition to the submission on CodeHS, just for your own safety. This class is an academic elective, so our final is going to be in that slot. It is on Wednesday, December 16th, during the second slot for the day, that is 11:15 through 12:15. Once again, final is an academic elective, Wednesday, December 16th, from 11:15 through 12:15, and I will be putting that messaging wherever it's relevant, just so that you guys remember. All right, so briefly discussing the stuff from Unit 1. This is all pretty foundational, so we should all have a pretty good understanding of this. What function do we use to display information on the screen? That is just our print function. Our 3 most common data types are int, float, and string. Int and float are both numbers, and string is what we use to store words. We can also work with Booleans. We learned about those later in the semester. Variables are essentially just a name we've given to a spot in our computer's memory so that we can store some information. Difference between user and programmer. The programmer is the person who writes the code. The user is the person who's interacting with it while it runs. Us as programmers, we're often going to play both of these roles at some point through our testing of our own code, but we need to anticipate that we're not the only ones who are going to be using our code. So we should make our code fairly error-proof so that someone else can't break it if they're running it. We use the input function to ask the user for information. And we can use typecasting to ask or to transform data into a different type. And typecasting is performed by using the name of the type. So whatever our type is called, so let's say I want to typecast to an integer, we're going to use an int, and this is a function. So we're going to put parentheses, and whatever value we want to typecast is going to go inside those parentheses. So if I want to typecast the user's input as an int, we're going to do int, and then input, and then our message to the user saying what we want them to enter. All right, our 8 mathematical operators. We have our plus, minus, wow, that's a terrible asterisk. Times is an asterisk, / is division. Regular old math. If we want to perform integer division, we can do a double / because this will result in a float. Where double / will result in an int. So if we want to get rid of decimal places for whatever reason, we can use that double /. We can use the modulus to find the remainder. We can use double asterisk to find the power, or to do exponents. That's 1, 2, 3, 4, 5, 6, 7. Our last one is the minus once again, but this one is a unary operator. This is negation. You only give one value and it will turn that value negative. And just make sure that you are able to do PEMDAS when presented with that kind of a problem. All right, that is essentially what you'll need to know for the Unit 1 sections. Anything about that? Any last questions about that before I let you guys work on today's assignments? Cool. Okay.